In this video, we'll talk about the problem number 6 in the IMO 2020. The problem states that assume that n is an integer with n greater or equal to 2, and let S be a set of n points in the plane such that the distance between any two distinct points in S is at least 1. Then there is a line L separating S such that the distance from any point of S to L is at least this constant C times n raised to power negative 1/3. And of course, by separating, we really mean L cannot be on just one side of all of the points in S. There must be points in S that lie on both sides of L. That is basically what they are saying in the parenthesis. Namely, some segment joining 2 points in S has to cross L, just to avoid all the points in S lying in the same side of L. The basic idea to prove this is that instead of considering the line that separates the set S, we're going to consider the line that is perpendicular to the line that separates S. And we'll look at how the points in S will projection onto this line. That is how we start with the proof. Okay, to begin with, let us fix some notations. We'll let delta be this quantity, this constant, times n raised to power negative 1/3 for simplicity. Later, we're going to show the C is precisely equal to 1/8. And at this point, we can pretend that we don't know this 1/8. Just take it as any fixed constant C that satisfies this property. Now let L be a line in R2. For point X in R2, we let X subscript L be the projection of X to L. Namely, if we draw a picture, if this is the line L and this is the point X, so we'll make a projection by making a line segment starting from X to L perpendicular to this line L. At this point, this projection image is denoted X sub L. And we can also define this notion for sets. For set S in R2, we let S sub L be the projections of all points in S to L. So for example, the set has point S and point Y and point Z. We're going to project every point in S onto this line L. So we get this YL and ZL. And S of L will be the collection of all projections of points in S onto L. So in this case, S of L is XL, YL, ZL if S is X, Y, Z. Okay, now with the notation set up, we'll talk about the desired situation of this problem. For the given S, in this problem, the set of endpoints the desired situation is that there exists a line in R2 such that if you look at S of L, the projection of point in S onto L. Okay, now let me draw a picture. Those dots denote the points in S, and we project them onto this line L. So for convenience, let me just draw two of them. Of course, there are also other projections. Now we look at SL, which is really a subset of the line L. If there exists two adjacent points, X, Y, in S of L, such that the distance we use absolute value to denote the distance. Between X and Y is greater or equal to 2 delta. Remember, we use delta to denote this quantity C times n raised to the power 1/3, negative 1/3. C times n raised to the power negative 1/3. So in this picture, if there exists such X and Y with distance at least 2 delta. Now, what does this mean to us? This means if we take the line L prime in R2 passing through the midpoint of the line segment XY and perpendicular to L. In this picture, if we take this blue line to be L prime, it's perpendicular to this L and passing through the midpoint of X and Y. Then every point in S will have distance to this L prime at least delta. Because the points x and y, the projection image, will have distance at least 2 delta. And we take the line perpendicular to x and y passing through its midpoint. The pre-images will also have distance to L prime at least delta each. And other points are even farther away. So every point in S will have distance to L prime at least delta. Okay, so this is a desired case. If this happens, then we are good. And now we'll focus on the case where this does not happen. Now suppose this is not the case, namely, for any line L in R2, the projection S sub L of S onto L does not contain two adjacent points, xy with distance greater or equal to 2 delta. Or in other words, any two adjacent points in xy in S sub L satisfy that their distance is less than 2 delta. And now our goal is to find the contradiction. Okay, now, how to find the contradiction? We begin by choosing 2 points, A and B, in S with the maximum distance, namely using mathematical notations. The distance between AB is the max of this set. Now we let S, now we let M denote this maximal distance. By the assumption of the problem that every 2 points in S have distance to each other at least 1. We know that this M, which is the maximum distance, should of course be greater or equal to 1. And it follows that the set S is contained in the intersection of dA and dB, the disks centered at AB with radius m respectively. The basic idea here is that because this S, the set of endpoints, does not have a shape, we're going to confine this S in a region with a shape. How do we do that? We choose 2 points with a maximum distance in S, and we make 2 disks centered at A and B respectively. And that will form a shape that contains S. With that fixed shape, it will be convenient for us to make estimates. So that is the idea. Now let us illustrate this with a picture. I just took the picture from the official solution of IMO. The red dots denote the set S. And we found points A and B whose distance measures the maximum distance between points in S. And now we make 2 disks centered at A and B respectively with radius precisely equal to the distance between A and B. It follows that every red dot will be contained in the intersection of those 2 disks. Because every red dot here will have distance to A and to B less than or equal to this maximum distance. So this is a picture. Now let the line L is a line passing through A and B. I look at the projection of S, those red dots, onto this line. It's contained in the line segment AB. So every point in S will project to this line segment. The projection image will not go outside of this line segment. Moreover, now here's the important part. The endpoints in S of L divide the line segment AB into at most n-1 parts. Why n-1? We have endpoints, but 2 of them are precisely A and B. They will not contribute to this division of this line segment AB. This line segment AB will be divided by the projection of the other n-2 points, which will divide A and B into at most n-1 parts. Because some of them may have the same projection image. So this is really at most n-1 parts. It might be less than n-1 parts. Each of length less than 2 delta. Now why less than 2 delta? Less than 2 delta because we are assuming the opposite. We assume that For any line L in R2, the projection S of L of S on L does not contain two adjacent points xy with their distance greater or equal to 2 delta. Or in other words, any two adjacent points in xy in SL satisfy their distance is less than 2 delta. So this is by our assumption that any two adjacent points xy in SL satisfy that the distance is strictly less than 2 delta. And this gives the following bound of M in terms of n and delta. So this bound is as follows: M less than or equal to n times 2 delta, which is 2n delta. We are using n instead of n minus 1 just for convenience. This is a more generous bound. But it doesn't matter because when n is big, n and n minus 1 will not have much difference anyway. So we will mark this inequality as equation number 1.